assistant has written sure there are, and then it stops. The next word hasn't been chosen yet. Whatever comes next isn't a sentence, and it isn't an answer, it's a single token. That one move is what makes these models useful, and it's also why they'll tell you something completely wrong with a perfectly straight face. The whole job is to look at everything written so far and guess what comes next. It writes one token. It sticks it on the end. Then it rereads everything to choose the one after that. That loop is the entire generation process. By the end, you'll know why it feels like intelligence, why it makes things up so confidently, and you'll have one running on your own machine. Here's the part that surprises people. It doesn't really pick a word at all. It assigns a probability to every token in its vocabulary, and those probabilities add up to 1. So plenty lands around 70%, many gets about 24, and a few stragglers sit down near 1. Then thousands upon thousands of others sit at essentially 0. Look at what that means, though. Countless would have been fine here, and so would several. It had an opinion about all of them, and then it committed to one. Let's try a cleaner one, where you already know the answer and so does the model. Paris is a city in blank. France comes out on top at 17%. But look at what else is in that list. There's and the, and which. Even Texas, down at the bottom because Paris, Texas is a real place. It picked France this time. It genuinely could have picked something else. So what's actually doing the guessing? It's a stack of layers that your tokens fall through, one after another. Inside those layers, there's nothing but numbers. Around 8 billion of them, for a model small enough to run at home. They're called weights. And nobody ever typed a single one of them in. There's a dial sitting on top of that list of scores, and it changes how the choice gets made. Turn it down and the top word wins almost every time, which is more predictable and honestly a bit lifeless. Turn it up and the lower rungs start getting a real chance. Livelier, but far more likely to wander somewhere it shouldn't. Same model, same prompt, completely different draw. Keep it low for code and facts, and push it up when you want prose. Now, here's a detail that makes people uncomfortable. The model itself keeps no memory of your conversation at all, none whatsoever. The conversation is its context, and it gets handed back again on every single turn. Inference engines do cache the internal state they already worked out, so it isn't redoing all of it from scratch, but nothing carries over on its own. What feels like a chat is really one document that keeps getting longer, and that document has a ceiling, which is what people mean by the context window. 8,000 tokens is a common size, though it varies by model, and you often choose it yourself when you load one. Once you go past what fits, the application has to do something, so it truncates or summarizes or drops the oldest parts. Here's the bit that gets misunderstood. The model didn't forget what you told it. Those words were never in the context it was handed. There's one more thing worth knowing about tokens, because that word is doing some quiet work. With this tokenizer, unbelievable comes out as 4 separate tokens. Many common words do fit into one, but less familiar strings get split apart, and code gets split much harder still. Rough rule for English: one token is about 3/4 of a word. So let's go back to those weights. Picture each one as a dial with a setting on it. The grid you're looking at is a few hundred. A small model you can run at home has 7 billion. Large frontier models can have hundreds of billions or more. Here's the part that still feels strange to me. Much of what the model has learned is sitting in where those dials ended up, rather than in code that anybody wrote. So how do the dials get set? You show the model the earlier tokens and let it predict the next one. Given the cat sat on them, it might say mat at 41% and floor at 22. The real text said mat. So you measure how far off it was. Then you nudge every weight a little, in the direction that would have made mat more likely. Ask the same sentence again, and mat comes back higher. Nobody wrote a rule anywhere. Now scale that up, because at the frontier the training text can reach trillions of tokens, far more than a person could get through in many lifetimes. The compute budgets are enormous. The runs use major GPU clusters, and large runs can take weeks or months. Which is exactly why you download one of these, instead of trying to make one. There's a catch though, because a model trained only that way isn't actually helpful yet. Ask the raw thing what the capital of Chile is, and you might get back what is the capital of Peru, what is the capital of Brazil. Perfectly plausible next words, and completely useless as an answer. So there are more stages after pre-training, starting with supervised tuning on written demonstrations of what a good answer looks like. Then a stage that pushes it toward the replies people actually prefer. RLHF is one well-known way of doing that part, and it isn't the only one, which brings us to the failure everybody complains about, and you can see the shape of it here. Ask which paper coined the term technical debt, and you get Cunningham, then Fowler, then Beck. None of that is a lookup. It's the shape of an answer that usually follows that shape of question. A tall bar means likely, and it has never once meant checked. So give the model the source text, ask for something you can verify, and keep a person on anything that matters. Everything I've described has to run somewhere, and this is where you get to choose. Send it out, and somebody else's GPU does the work, which means your prompt leaves the building. Or run it right here, on the machine in front of you, and the prompt stays with you. Same request, same idea, just a different building. 4 reasons people keep this local. Privacy, because the prompt never goes anywhere. Cost, because no provider is charging you per token. Offline, because it works on a plane or in a lab with no network. And control, because you keep the exact same weights tomorrow, whatever anybody else deprecates. Now, the honest trade-off, because a 7 billion model on your laptop is not a frontier model, and for genuinely hard reasoning, the big hosted ones are still better. Memory is your first budget, and RAM is the easiest place to start. These are rough numbers for quantized models. 8 gigs runs a 3 billion model comfortably. 16 puts you in the sweet spot at 7 or 8 billion. 32 opens up 13 billion, or a much longer context, and 64 and above gets you to 30 billion and beyond. These lines move depending on your VRAM, your context length, and your quantization. So check before you download, because once it starts living on disk instead of memory, performance falls off a cliff. Worth being clear that parameters are not megabytes, because parameters are just a count. Weight storage is that count multiplied by how wide you keep each one. So 7 billion at 16 bits is around 14 gigs. Squeeze every number down to 8 bits, and you're at 7.5. At roughly 4.5 bits, you land near 4.4. That's only the weights though, because running it also costs you context and cache on top, so leave some headroom. That squeezing is called quantization. And here's what it doesn't do, because it doesn't throw away any layers. Every one of them is still there, and it simply holds their weights at lower precision. For GGUF models, Q4KM is a very common starting point. It cuts the memory dramatically, and for a lot of everyday work, the quality loss can be small. Push the precision lower and you save more, but how much you give up really depends on the model and what you're asking of it. Right, so let's actually run one of these, and it only takes 5 moves. Install LM Studio, search for a model, and download a quantized build of it. Then load it up and start typing. No terminal, no Python, no account to create, and no card to hand over. The obvious question is which model? Llama is the general purpose choice, with the biggest community behind it. QN is strong if you write a lot of code, and Mistral is small and quick. Vi and Gemma are worth a look too, especially if your machine is tight. For a first model, 7 or 8 billion parameters at Q4KM is a strong starting point. Get something running, then trade up. When it loads, 4 numbers are worth watching. File size on disk, which is just what you downloaded. RAM in use, which has to stay under your total. VRAM in use, which tells you how much made it onto the GPU. And context length, which is how much it can hold at once. If memory is tight, pick a lower bit quantization or a smaller model. You trade a little quality for a much lighter footprint and usually better speed. Now stop testing it and actually use it. Ask it to explain something you only half understand. Ask it for code with a real endpoint in it. Throw a genuinely hard question from your own work at it. Keep an eye on the tokens per second, because that's your generation speed. And do check what it tells you, because a small local model is confident in exactly the same way an enormous one is, where the arithmetic happens changes everything. A CPU has fewer general-purpose cores, and honestly, it works. It's just patient about it. A GPU has many parallel compute units, and this workload is mostly large matrix multiplications, which is precisely what those units were built for. So push as many layers onto the GPU as its memory will take. Ask for more than it has, and the remaining layers run on the CPU. You'll feel the difference immediately. Here's my favorite part of all of this. One toggle, and the model stops being an app and becomes a server. Localhost port 1234. It speaks the same shape of API as the hosted ones do, which means it stops being a special case and becomes just another endpoint, which matters because code you've already written works against it, and only 4 things change. You point the base URL at your own machine, name the model you loaded, send the same message shape you always send, and read the reply the same way. Authentication is optional by default here, so the key can be any string until you turn it on. What comes back is a real completion, off your own hardware, with no external network hop and no bill at the end of the month. So where does that leave you? 3 things, really, starting with the next token, which is the one operation sitting underneath all of it. A local model running on your own hardware with no token bill. And a local API, an endpoint your own code can call. That's the whole stack, and it's sitting on your desk. One last thing, because we skipped the most interesting part. I told you it reads the context, but I never told you how. Each token can look back at the tokens before it and work out which of them actually matter. Take a sentence like "down by the river bank." By the time the model reaches bank, the word river is what settles which kind of bank you meant. That mechanism is called attention. It's one of the key mechanisms that makes transformers work. Next time the transformer